Hello everyone, this is Dariush Khezrimotlagh from Pennsylvania State University, and I'm going to present how to deal with a small number of DMUs in data envelopment analysis. Let us suppose that we have an example of 10 international Iranian airports with 3 inputs and 3 outputs. We would like to measure the performance of these airports. As can be seen, none of the rules of thumb are satisfied here. For example, 10 is not greater than equal 2 multiplied 3 plus 3 or 12, and similarly we need at least 18 airports, which is not possible in this case. If we want to decrease the number of variables, we also miss some of the information which may not support our purpose of this study. When the number of DMUs are not enough in comparison with the numbers of inputs and outputs, most of DMUs may be introduced as best practice DMUs with the DEA score of 1. For example, if we apply the radial variable returns to scale DEA model, all DMUs become best practice airport except airport 5. From the previous study, one may mistakenly use the super efficiency model to measure the performance of these airports. However, as Bunker and Chen in 2006 and many others discussed, the super efficiency models are not for measuring the performance of DMUs nor to rank DMUs. One solution to deal with the small number of DMUs is proposed by Khezrimotlagh, Cook, and Zhu in 2019, and I'm going to illustrate that methodology in this presentation. The methodology is based on a fact that a DMU has the highest performance in comparison with any other DMUs if its corresponding feasible neighbors are more efficient than the corresponding feasible neighbors of any other DMUs. So here neighbors for an output is defined as decreasing small amount of that output. If we have 3 outputs, we can have a cube to define the neighbors. Similarly, for an input, we can increase that input value. By such an approach, we make sure that the defined neighbors are always feasible. For example, if we have several banks with 2 inputs and 2 outputs, such as asset and equity for inputs and revenue and profit for outputs, for a bank that lies on the best practice frontier, decreasing a small proportional amount of the revenue or profit should not cause a huge effect in the efficiency score of that bank. That is, its DEA efficiency score should still be very close to 1. Similarly, increasing a very small proportional amount of the asset or equity should not cause a huge effect in the DEA efficiency score of that bank. Now assume that we want to compare 2 banks which lie on the best practice frontier. DEA assigns the unit score to both banks. That's from conventional DEA suggestion, both DMUs are best practice because no improvements are possible in their inputs and outputs according to the available observations. Like this example, we are not able to improve DMU L as it's already on best practice frontier. So if we have 2 banks lie on the best practice frontier, which one of the banks has a stronger neighbors? If a very small proportional and commensurate decrease or increase happens in outputs or inputs, do the two banks still have the same DEA efficiency scores? What are the effects of a very small change in the inputs and the outputs of the two banks? Which one of the banks is less sensitive to a very small change in its inputs and or outputs? These questions lead us to measure the DEA efficiency scores of neighbors of the two banks. We can now reasonably conclude that a bank which has a higher average efficiency scores for their defined neighbors in comparison with that of the other banks obtains the best performance. If average efficiency scores of the defined neighbors of both best practice banks are the same for every value of delta or the neighbors that we define here, we conclude that both banks have the same strength in their inputs and outputs. Let's get back to the radial DEA model. For an inefficient DMU in the output space, we can radially improve the outputs of DMUL to reach frontier to become best practice DMU. As can be seen from the model, the optimal objective shows us the possible increase in output values at the level of input values. When a DMU lies on the frontier, phi star is equal to 1. What we propose is that corresponding to DMUL, we define the neighbors which are introduced by a proportional change in the variables of DMUL, as can be seen from the model. Here Ti minus and Tr plus can be 0 and 1. As Ti minus can change from 0 to 1 for each input and output, we will have one of the neighbors. This DMU is the most efficient neighbor of DMUL. That means all the other neighbors have a DEA efficiency scores between the worst efficient neighbor and the best efficient neighbor. So what's the efficiency of this DMU? According to the theorem, for a DMUL whose CRS efficiency score is phi star L, the corresponding CRS score for the weakest delta neighbor is phi star L multiplied by the ratio of 1 plus delta over 1 minus delta. This score is called as adjusted score for DMUL. So now let's program this model by Excel. Since we have a small number of DMUs, the Microsoft Excel software is very useful to explain how this methodology works. Here we have inputs and outputs of 10 DMUs in an Excel sheet. We consider two cells for two indexes, one for selecting a DMU and one for selecting its corresponding neighbor. The first neighbor is DMU itself. For example, the first DMU, DMU A, has these variables. As we change the index for neighbors, the third output decreases by 5% the value which we assume for delta. We can change it any value between 0 and 1. Here we have 6 variables, so 2 to 6, that is 64 neighbors we can define. The binary variables can make it easier to understand how these neighbors are defined. So the first neighbor, as we can see here, all TIs are 0, so we have the DMU itself. For the second neighbor, the third output is decreased by 5%. The fourth neighbor, the second and the third output decrease by 5%, and so on. So a DMU which is evaluated, we have it here. To define
the evaluated DMU, we can look at the right hand side of the constraints. Is 1 plus delta times 2 Ti minus multiplied by XIL. So XIL here shown by the first input according to the index of the DMU. So when we select DMU 1, it gives us 19.39.3. If we select DMU 2, the input of B is selected. 1 plus, so we have 1 plus here. Delta Ti negative. Delta is 5%, we have it here. And to have Ti, for the first input, we need the binary corresponding to the first input. It can be 0 or 1. Similarly for the next input and the next input, and also for output. Here we can simply define the DMU which is under evaluation. The linear combination of inputs, which we can define it as sum product of the inputs to the changing cell lambdas. And similarly for the second input, sum product of the second inputs to lambdas for the third inputs, and for the outputs similarly we have sum product of the third outputs to the lambda. For example, if I assign 1 for lambda 1, we have exactly the variables of the first DMU. As soon as I change this neighbor, so we can see the right hand side is changed, which is exactly the same as what we have here. Sum lambda shows the sum lambda equal to 1. This is the variable returns to a scale condition. So pretty everything now is ready for us. So here from data we can use solver. So as we can see here, set objective is y15 that I have it here. We have a maximizations, this is outward orientation, and the changing cells we have seen here, phi is a changing cell, and lambdas, this is variable returns to a scale constraint. The linear combination of input should not exceed the evaluated DMU's value. So here we have the left hand side less than equal the right hand side, which is exactly equal to the values of the DMU which is under evaluations, and the output should be greater than equal, so the left hand side are greater than equal, and make unconstrained variables non-negative, and we choose simplex method and we solve the model. So as we see, the first DMU lies on the best practice frontier. Here we can write the procedure. Instead of going to data and click on solver and then run the solver, we can just write the procedure that I already wrote here. By Visual Basic for application, we can just use solver solve, user finish true, and then based on the number of DMU and number of neighbors, we can put the result in these provided cells. Now if we click on run, we automatically have the optimal value of phi here, and of course we can continue the evaluation process. We can similarly do for the next DMU. So we run the model, we have again the same situation, but for the second neighbor we still have the unit score when 5% the third output is decreased. This evidence shows us this neighbor of DMU B lies on the weak efficient frontier, and similarly for the next one, these neighbors of B also lies on the weak part of the best practice frontier. Even we decrease both of them, we are still on the weak part of the best practice frontier. So now we have all evaluated DMUs and their corresponding neighbors. So we can calculate the average of these efficiency scores, which is not equal to 1. So here we have the outcome and the rank of each DMU. The highest performance belongs to DMU K. It shows the inefficient neighbors of K are more efficient than the neighbors of any other DMUs. From this approach, we measure the performance of each DMU without any additional information. We only use this fact that a DMU has the highest performance in comparison with any other DMUs if its corresponding feasible neighbors are more efficient than the corresponding feasible neighbors of any other DMUs. I hope you enjoyed this presentation. For more information, see Khezrimotlagh, Cook and Zhu 2019. Thank you and bye bye.